Hi there. Today we are investigating the concept of constant velocity. To do so, we will do this with the help of Newton's second law, force is equal to mass times acceleration. If constant velocity exists in a system, then the net force on the system will be equal to zero. In an attempt to observe constant velocity right here in my own home, I took a basketball and rolled it across my coffee table from good old IKEA. My friend videotaped it, and then we uploaded it to Tracker to analyze our example. Here's my example. There was a couple things I needed to do in Tracker to properly analyze my realistic example, is better to say. First, I set the calibration stick, which is right here, to 0.25 meters, which is the average diameter for a basketball. And then I took the origin of the axes, which are right here, and attempted to place them at about the origin or the center of mass in the basketball. I also made sure that the axes were basic as I always assume them, which is that positive x is in the right direction, which is over here, and that positive y is in the upward direction. Overall, I observe about 0.708 seconds of the ball's velocity, and that is between these two black arrows, and I made sure to record and analyze the section after my hands leave the ball and before that the ball goes off the table. As you can see over here in the graph, the ball's velocity is almost constant, and here it's a position versus time graph. There's a few fluctuations in between which have to do with my placement of where I put the origin of these little diamonds as the ball rolls along the negative x-axis. To compare the real-life example to a computational model, I used the basketball's mass, initial velocity, initial position, and final observed time in my VPython code. With this, I was able to predict the object's future motion velocity. There was a few parts of the VPython code that I want to explain really quick. This line, ball.position equal to vector plus 0.012, 0, 0, and ball.vl equal to vector negative 1.0500, are both really important. These are for the initial conditions, and I plug these numbers in based off the Tracker graph. T is equal to 0 because in the Tracker video, I'm assuming that the ball is leaving my hands at initial t is equal to 0. That's the initial time that it's leaving. For the second major part of the coding for VPython, I have fnet is equal to 0, 0, 0, because constant velocity can only exist in a system where the total force and acceleration is equal to 0. This is our main assumption with the computational model. We have to assume fnet is equal to 0 in order to obtain some kind of constant velocity. The velocity equation is the next line of code defined. And then over here, the next line, the next really important, is the position equation. And this line right here, advance the clock, t equals t plus delta t. This is to advance time as the code runs, so each time, it's like a loop. Every time this happens, the ball will move forward in its velocity and its position. The next important thing I decided to show you would be how my code runs. So as you can see here, the computational model pretty well represents what happened with the basketball. This ball right here, that's magenta, moved towards the left, which is the negative x-axis. And here it shows a constant slope in the negative x, or in the positive x and negative y direction. And this graph right here shows constant velocity. And I compared these two in this model versus experiment graph. The dotted line is the same line from the computational model, which shows perfect constant velocity, and then the blue line is my experimental position, which is from Tracker. It's the same line from Tracker, and as you can see along the line, there's definitely some fluctuations. It's not perfect, and these can be due to just any errors that I made in Tracker, such as putting the axes not in exactly the origin of the basketball. It can be not labeling the center of mass along the negative x-axis correctly as the ball moves. That, and since, I did it in it's a real life example, the basketball moving along the table. There's other things that can come into play that clearly will note that constant velocity was not going to be able to, it's not expected fully in real life. We have to assume that there's no net force, and friction can exist and drag force can exist, gravity exists, all those things exist in real life. So that's my lab. I think I got pretty close, with the experimental position and the model with the basketball along the table. It was really fun to explore this, and it was cool to see that constant velocity doesn't exist, or at least didn't exist in this example perfectly, but it came pretty close, and that was really cool. Equations I used. First is the velocity equation, which is V final is equal to V initial plus F net divided by mass times delta T. Since F net is equal to 0, this entire section, F net divided by m times delta T, will be equal to 0, and then the equation just becomes velocity final is equal to velocity initial. Since the velocity initial is negative 1.05, that's also then equal to velocity final, which then in turn is equal to the average velocity, because this is supposed to be a system with constant velocity. Then the position update function is R final is equal to R initial plus velocity average times delta T. Delta T is 0.708 seconds because that's the duration of the ball's motion. That's times velocity average, which is negative 1.05. And that's plus the initial position, which we know is 0.012 from our tracker graph. And that all gives us our final position.